All right, so this is our last type. We have y-axis and x equals. But we're going to mix it up a bit, and we're going to go from a and a, just so we can throw two videos into one, so you don't have to watch another one. It's not that bad. So since we have x equals, that means we're going to be using dx dy for our ds. So our x equals square root of a squared minus y squared. And so we need to write that as a fraction so we can use chain rule. So then dx dy, which is our x prime, is 1/2 a squared minus y squared negative 1/2 times, and it's chain rule. So we need to multiply now the derivative. Okay, so that would become negative 2y. The 2's cancel, and we end up with negative y over square root a squared minus y squared. Let's double check this. The 2's cancel, y goes on top, that goes on the bottom with a square root. And we're putting this with a square root because the next step is to square it. So after we square it, we're going to end up with dx dy squared equals y squared a squared minus y squared. And the next step, after we've squared it, is we add a 1. So 1 plus 1. And so if you remember these from before, we need to make this a nice perfect square. So if you see the fraction in the 1, that's one method to do that, unless it's an easy one to substitute with u substitution. So we're going to add top and bottom. So this is y squared. We'd multiply this one by a squared minus y squared. I'll put that in green. So a squared minus y squared over a squared minus y squared. And hopefully you're pretty quick at these from partial fractions from before. So you would see that the y squareds will cancel, and then we would just get a squared on top, which is a good sign. That's a nice perfect square. And then the bottom we have a squared minus y squared. And then that's all we can do. So now when we put our 1 plus dx dy squared, don't get discouraged because the bottom didn't go away. It usually will take care of itself. So now that's our partial of our ds, and we're going to throw a dx on the end. So if we want to write it, we have ds equals a over the square root of a squared minus y squared dx. So since we took it, see? dy. Since we took it with respect to y, we have to write dy. We are using this one. We probably should just circle it just to know which one we're using. All right, so we now have s equals the integral from 0 to a, because everything is in terms of y here, so we're good, 2 pi x ds. So we get 0 to a, put the 2 pi outside, 2 pi, 0 to a. And since this is already in terms of y, we do need to plug our x in. A squared minus y squared. And then our ds. See, and that's why I was saying everything takes care of itself. Hopefully you see that now. And so those cancel. And you're like, oh, well, this is a nice integral. Yep. 2 pi integral 0 to a dy. And since a is not a variable here, the integral is extremely quick. It's 2 pi a. We just tack a y on it, a and 0. Plugging those in, we get 2 pi, bracket, a times a minus a times 0. And so that is just 2 pi a squared. Now this should look familiar to you, and I'll show you where this comes from. So that is our shape. I used 4 because, well, I can't just plug in a. A is already being used here. So if I go back to our main shape, that is our graph, and so it's a quarter of a circle. So if I rotate it, it makes a hemisphere. So what we just found was that surface area for the hemisphere minus the circle, of course, on the bottom. So if we were to double that, it would be the top surface and the bottom. So if we were to double this, surface area of a sphere would just be 4 pi a squared. And what is our a here? It's the radius. That's what it is. See, we're going from 0 to a. So if you were to multiply this out, it would be a circle. X squared plus y squared equals a squared. So a is our radius here. So if you took that that circle, all we have to do is take a quarter of a circle and rotate it and double it. We just found the formula for the surface area of a sphere. Pretty cool, huh?